Good morning. In the last classes, we have been looking at asymptotic algorithm analysis, right? So, in asymptotic algorithm analysis, it is actually an estimation technique where we try to estimate the running time or time complexity of algorithms. Okay, as the input reaches very large numbers. Okay, so it is an estimation technique and it is not like implementing and finding out the time taken. Now, in order to do asymptotic algorithm analysis, what we said is the first step is to identify the basic steps. Okay, so we went through the process of identifying the basic steps. How many basic steps are there? We identify them, we sum them, and we write it in terms of some function of input generally, say some fn. Okay, so once we count the number of basic steps, now that has to be represented in terms of what is known as an asymptotic notation. And we also came across, or we also said there are three different asymptotic notations which are commonly used. One is big O, big omega, and big theta. Right. So we also saw the definition of big O notation. So we said any function fn can be said to be order of gn if there exists some positive constant cn and not such that you can write fn is less than or equal to c into gn for all n greater than or equal to n naught. So we also saw this particular example, right? So we say fn is 3n plus 2. We can write it as order of n. N is our gn. Okay. So we can write it like this only if it is possible to identify positive constants, some c. C is 4 here, and we say 3n plus 2 is less than or equal to 4n, and this is actually true for all n greater than or equal to 2. It is not true for 1. So this function is true only for n greater than or equal to 2. And we also said this big O notation is actually, you can say it is an upper bound on the time complexity of our algorithms. It acts as an upper bound. That is our function which we found 3n plus 2 is actually the number of basic steps we counted. So we can say it is like that. And 4n is actually an upper bound on this particular function. So our algorithm has a running time which has 4n as the upper bound. It cannot grow any further than that. That is the meaning of the algorithm, meaning of the notation. Okay, so till this point we have discussed. Now we'll look at a few more examples, okay, of how we convert a function fn into a big O notation. Okay, now here we have 3n plus 3 is equal to order of n. So again 3n plus 3 we are writing in as order of n. Okay, so we can write in this terms only if we find two constants c and n naught, such that you can write 3n plus 3 less than or equal to the constant into n for some n greater than or equal to n naught. So here we are writing 3n plus 3 is less than or equal to 4n. So what is the n values for which this is true? So what if n is equal to 1? So when n is equal to 1, we have 3 plus 3 is 6 less than or equal to 4, which is not true. So let us try with 2. Uh, so 3 into 6 plus 3 is 9 less than or equal to 8, which is also not correct. So we go on to 3. So 3 into 3 is 9 plus 3 is 12. Okay, 12 less than or equal to 12 we get, which is correct, right? So we can say, we can write 3n plus 3 or fn is order of n for positive constants. C is equal to 4 and n greater than or equal to 3. Okay, so this is how we find the constants. Similarly, we can look at other examples. Again, here we can say 100n plus 6 less than or equal to 101n. For with trial and error, we find values of n for which this inequality, that is 100n plus 6 less than or equal to 101n. For what values of n is this true? So with trial and error, we find the values of n. So similarly, for Even quadratic equations, you can say 10n squared plus 4n plus 2 is order of n squared. So how can you say that? You have to identify some constant c and n naught. Here c is 11 and n greater than or equal to 5. Again, it is through trial and error that we find. It can be done for exponential functions also. Okay, so this is an exponential function. 6 into 2 raised to n plus n squared less than or equal to 7 into 2 raised to n. Again, you find out values. Okay, so this is how you identify C and N naught. So if you look at this example, 3n plus 3 is order of n. So we said C is 4 and n is 3. Now these values are actually not unique. You can also say, let us say, I can write, so we can actually also write 3n plus 3 is our fn is less than or equal to some constant c into n, that is order of n, right? Okay, now we can also that is we can solve for c and n naught in this way also, that is we write it like this, and we say we try different values for n. Say we say n is equal to 1, and then so now when n is equal to 1, we can write 3 plus 3 is 6 less than or equal to c. Okay, so here we have got for c we have got a value c greater than or equal to 6. Okay, and for n is equal to 1 or n equals 1 or greater, this can actually be true. So in this particular solution, we said c is equal to 4 and n naught is equal to 3, right? N naught equals 3. Okay, we can also write c greater than or equal to 6 or c equals 6 and n greater than equal to 1. So for this condition also, you can say when you say order of n, for these two values of c and n also, you can say fn is less than or equal to c into n. Now how it differs is, if we actually draw a graph like we did earlier. So we said we have 3n plus 3 is aligned somewhere like this. So we are saying this is 3n plus 3, and we can say 4n is our other function. So I'm saying, since there is no y-intercept and drawing through the origin, and I'm saying this is 4n. Okay, and for n greater than or equal to 3, this must be 3. Okay, so fn is less than or equal to c into gn for n greater than or equal to n naught. So n naught here is 3. So this 4n actually is an upper bound for 3n plus 3. Okay, that is what we said here. Now if you consider these constants again, so here we can say c is 6, right? So our bounding function gn is, sorry, it is 6n, not 4n, it is 6n, right? So again it passes through your origin, but its slope is slightly higher. So we'll draw some graph like that. Okay, let us say this is 6n. Okay, so you can also say 6n is the upper bound for 3n plus 3, but in this case the value of n will be slightly different. N is equal to 1, so or n greater than or equal to 1, this is true. So basically what we mean is for this particular function 3n plus 3, you can have a bounding function. So it could be either 4 or 6, and the constants are immaterial, but what we are saying here is the bounding function, the upper bound is the order of n. Okay, it is the order of n. The constants are not really that important. Okay, so the bounding function is, it is n. Okay, so that is the idea. So what we are saying is Cn and not are not unique values. You can have different values of Cn for which this Fn less than or equal to C into n can be satisfied. Okay. Now, if we look further, another thing which we want to discuss is 3n plus 3 is equal to order of n squared. Okay. So, in order for that to be true, we can say 3n plus 3 is less than or equal to 3 into n squared, and it will be true for n greater than or equal to 4. With trial and error method, we can find n also. So, what that means is, uh, look, this is 3n plus 3 is our fn. So, for n greater than or equal to 4, we can say that we have n squared is also a bounding function. N squared is actually quadratic function. It is not linear. So, we'll draw it like this. So, this is 3n squared. And for 3n squared can also, we can say it is a bounding function for n greater than or equal to 4. So, it is only after this point that it becomes, so this is 4. N greater than or equal to 4, 3n squared becomes a bounding function. So, anything greater than n can be a bounding function, but n is the closest bounding function to 3n plus 3, and it is that which we usually say when you say 3n plus 3 is order of n, that is a closest bounding function. But we also can say 3n plus 3 is order of n squared, but that is not a closest bounding function. Okay, closest ആയിട്ടുള്ളത് n ആണ്. Okay, that is what we need, right? Similarly, here you've got one second. Okay, here you got 10n squared plus 4n plus 2 is actually order of n squared. That is a closest bounding value. Okay, closest boundary. It is a quadratic boundary. But you can also write order of n raised to 4. N raised to 4 is also an upper bound, but the closest upper bound will be order of n squared. That is what we mean. Okay, okay. In order to say that, you have to be able to write this, and this is true for n greater than or equal to 2. But although we can say for this particular function, n raised to 4 is an upper bound, you cannot say 3n plus 3 is not order of 1. Okay, order of 1 എന്ന് പറയുമ്പോൾ how can you draw it? Order of 1 means uh, fn is a constant, so y is equal to 1 order of 1. It is like this. So our initial function was something like this. So this particular y is equal to 1, okay, or fn is equal to 1, order of 1 എന്ന് പറയുമ്പോൾ ഈ constant value ആയിരിക്കും. That cannot, this is not an upper bound for this line, right? It is not an upper bound, it's lower than that. So you cannot say 3n plus 3 is order of 1. Similarly, you cannot say 10n squared plus 4n plus 2 is not order of n also. It has to be at a higher level. But you can say for this function 10n squared plus 4n plus order of n raised to 4 എന്ന് പറയാം. The closest bounding function is order of n squared. Okay, I hope this BigO notation is clear with these examples. Okay, so these are some of the running times which we will come across. Order of 1 means constant running time. Okay, and then you have linear, quadratic, cubic, exponential. So when we analyze different algorithms, say sorting algorithms or other algorithms which we come across, these are some of the common uh, orders which we come across. Okay, and you also have graphical representation of these. So order of 1 will be some constant. Say order of 1 is something like this, right? You have a constant running time parallel to your x-axis. So, okay. You have log n, and log n. So just get familiar with the different functions and how each of these looks like. Okay. So this is about order of BigO notation. Now we are moving on to big omega. Big omega, we'll just see what the definition is and what the meaning of big omega is. We will not be going into exercises or examples. Okay. So big omega, simply speaking, is actually the lower bound of Fn. Earlier we had talked about upper bound, and big omega is actually lower bound for a particular function. Okay, so here you can say Fn as omega Gn if there exists positive constants Cn and naught, is that Fn is greater than or equal to C into Gn for all n. Earlier we had less than or equal to, here you have greater than or equal to some constant C into Gn for all n greater than or equal to n naught. Okay, so you can, if you look at this example, 3n plus 2 is omega of n. So you can write 3n plus 2 is greater than or equal to 3n. And with trial and error, we can say that n greater than or equal to 1. So this condition is true for all n greater than or equal to 1. And graphically representing this, so we had drawn graphs earlier also, n here and maybe fn here. Then so 3n plus 2 is, it has a y-intercept, so we'll draw something like this. So 3n plus 2 is this, and 3n is actually a lower bound. Okay, and this is true for all n greater than or equal to something like this. It's a lower bound, so you can say it will never get, the boundary will never get lower than this. So that is what a lower bound is. Okay. So just like we did earlier, for each of these functions, we can also define lower bounds. So the only thing we have to do is, earlier we said 100n plus 6 is less than or equal to say 101 into n. Here we are saying, we are assuming this constant is 100, and appropriately we can find n values also. So that is what is we have done for all these examples also. So basically omega means it defines a lower bound for the running time. Okay, and theta is actually defines both an upper bound and a lower bound. That is what theta is about. Okay, so we say Fn is theta Gn if there exists three positive constants C1, C2 and naught, such that this our Fn is between C1 Gn and C2 Gn for all n greater than n naught. So it actually defines both an upper and lower bound for Fn. Okay, so here if 3n plus 2 is theta n, if we want to say like that, we have to find that is, we have to find C1, C2 and n naught, for which we can say 3n plus 2 is greater than or equal to 3n, and 3n plus 2 is less than or equal to 4n. So graphically representing, we can say 3n plus 2, we draw a function. So maybe we have some, okay, we are saying 3n plus 2, this middle one is our 3n plus 2, and we have got both a 4n which is an upper bound and 3n which is a lower bound. So if you are able to write like this, then we can say 3n plus 2 is order of n. You have both an upper bound and lower bound. That is what big theta is. Okay, that is the meaning of it. Okay, now we have a few exercises. You can try out these 6 exercises are there. First of all, you have to go through and find the basic steps, and you can express the basic steps in terms of n. You can write fn, a function of n, and then you can represent fn in big O notation. We are not going to talk about big theta and big omega, that we got the meaning of it, but for these worked out examples, you have to find BigO notation for each of these different exercises. Okay, so that's it for today.